Welcome to today's problem walkthrough. We'll be tackling LeetCode problem number 999, available captures for Rook. In this problem, we'll explore how to determine the number of pawns a Rook can capture on a chessboard, given certain constraints. Let's dive in. In this problem, we are working on an 8x8 chessboard where there is exactly one white rook, denoted by the letter R. The board may also contain other elements like empty squares, represented by a dot, white bishops, represented by B, and black pawns, represented by P. These elements are organized in an 8x8 matrix, referred to as board. The rook moves as it does in a standard chess game. It can move vertically or horizontally across the board, stopping if it encounters another piece or the edge of the board. If the rook moves to a square occupied by a black pawn, it captures that pawn. The goal is to write a function that calculates and returns the number of black pawns the rook can capture in a single move, considering all possible directions it can take. Let's look at an example to understand this better. Here, we have an 8x8 board where the white rook is positioned at row 2 and column 3, using zero-based indexing. This is reflected in the input matrix. There is also a black pawn located directly above the rook at row 1, column 3. Since the rook can move vertically upward, it can capture this pawn. No other pawns are in reach because all other squares along the rook's possible paths are either empty or blocked. Based on this setup, the function should return an output of 1, indicating that one pawn can be captured. In another example, the board is more complex. The rook is located at position 3, 3, again using zero-based indexing. However, in this scenario, all of the rook's potential paths are blocked by white bishops, represented by B. These bishops prevent the rook from moving either vertically or horizontally past them. Since the rook cannot reach any black pawns, the number of pawns it can capture is 0. Therefore, the function should return an output of 0 for this example. Now, let's examine a scenario where the rook can capture multiple pawns. Here, the rook is positioned at 2, 2. Looking at the board, the rook has 3 pawns it can capture. There is a pawn directly above it at 1, 2, another pawn directly to the right at 2, 3, and a third pawn directly below at 3, 2. The rook can move in these directions without being blocked, so it can capture all 3 pawns. This means the function should return an output of 3, indicating that 3 pawns can be captured in this case. To summarize, there are certain constraints and edge cases to consider. First, the board is always an 8x8 matrix, and each square on the board must be one of the following: a rook, R, a pawn, P, a bishop, B, or an empty square, dot. Additionally, the board is guaranteed to contain exactly one rook. Edge cases include scenarios where the rook is entirely surrounded by empty squares, meaning it cannot capture any pawns, or situations where the rook is blocked on all sides by bishops, also preventing any captures. Finally, there are cases where the rook may be able to capture multiple pawns in different directions. Edge cases are critical to understand. For instance, the rook may be completely surrounded by empty squares, leaving it unable to capture any pawns. Alternatively, bishops might block all paths of movement, resulting in no captures as well. On the other hand, there are situations where the rook has opportunities to capture multiple pawns in different directions, such as vertically, horizontally, or even both. These edge cases underscore the importance of carefully analyzing the board layout to determine the rook's potential captures. To begin tackling this problem, one straightforward approach is the brute force method. Here, we start by scanning the entire 8x8 chessboard to first locate the position of the white rook, denoted as R. Once we know where the rook is, we evaluate its potential moves in all 4 cardinal directions: up, down, left, and right. While scanning in each direction, we carefully track what the rook encounters. If it finds a black pawn, represented as P, that pawn is a valid capture, and we increment our capture count. However, if the rook encounters a white bishop, labeled as B, it cannot move past it, as the bishop blocks further progress in that direction. Similarly, the rook's movement is limited by the edges of the board. The key insights here are that the rook moves exclusively in straight lines along rows or columns, bishops act as obstacles, and black pawns are the targets we aim to capture. In terms of computational complexity, this brute force approach operates with a time complexity of O(n²), which is manageable since the board size is fixed at 8x8. The space complexity is O1, as no additional data structures are required. This brute force approach is conceptually simple and avoids unnecessary computations by focusing only on the rook's valid moves. However, we can optimize this further. Instead of separating the process into two distinct steps, locating the rook and then evaluating its moves, we can merge these into a single traversal. In this optimized implementation, as we traverse the board to locate the rook, we simultaneously check the potential moves in all four cardinal directions. This eliminates the need for redundant scans. To streamline this even further, we can use a helper function to handle directional movement checks, which simplifies the logic and makes the code more modular. The key steps in this approach include traversing the board to locate the rook, evaluating its moves in each direction as soon as it's found, stopping the evaluation when encountering a bishop or the edge of the board, and incrementing the capture count for every black pawn encountered. Once we've completed this process, we simply return the total number of captures. The optimized approach maintains the same time complexity of O(n) squared as the brute force method, since we still traverse the board and check in all four directions. However, given the fixed 8x8 size of the board, this is effectively constant in practice. The space complexity remains O(1), as no additional data structures are needed. What sets this approach apart is its reduced redundancy. By combining the search for the rook and the evaluation of its moves into a single traversal, we simplify the logic and improve efficiency. Additionally, the use of a helper function for directional checks makes the code cleaner and easier to understand. While alternative methods, such as separate scans or pre-computing all possible moves with extra data structures, were considered, they add unnecessary complexity given the fixed size of the board. The chosen strategy strikes the best balance between simplicity, efficiency, and clarity. It ensures the solution is both easy to implement and highly effective, making it the most practical choice for this problem. To solve this problem, we need to determine how many black pawns a white rook can capture on an 8x8 chessboard. The board is represented as a 2D array where each cell contains either a white rook, R, a black pawn, P, or an empty space, dot. The rook can move any number of squares either horizontally or vertically, stopping when it encounters another piece or the edge of the board. The first step in solving this is to locate the rook on the board. By iterating through every cell in the 8x8 grid, we can identify the row and column where the rook is positioned. Once we have its coordinates, we simulate movement in the four cardinal directions: upwards, downwards, left, and right. Now, the goal is to check for any pawns that the rook can capture in these directions while stopping at obstacles or the edges of the board. To simulate the rook's movement, start from its position and examine each direction individually. Moving upwards involves decreasing the row index while keeping the column constant. Downwards means increasing the row index, again keeping the column fixed. For horizontal movement, we decrease the column index for leftward motion and increase it for rightward motion while leaving the row unchanged. In each direction, we continue this movement until encountering a black pawn, which can be captured and counted, another piece that blocks the path, or the edge of the board. To track the total number of captures, we maintain a counter that increments each time a pawn is captured. After exploring all four directions, the value of this counter will represent the total number of pawns the rook can capture, and this value is returned as the result. It's important to note that the rook's movement is constrained to rows and columns, which simplifies the problem to just 4 linear searches. The chessboard is represented as a two-dimensional array, which allows us to directly access any cell using its row and column indices. This representation is both intuitive and efficient for simulating the rook's movement. To count the number of pawns captured, we use a simple integer variable, increment, whenever a pawn is successfully captured. Let's consider an example to solidify our understanding. Suppose the board is given as follows: the rook, R, is located in the middle of the board at position 2, 3, and there are pawns, P, above and below it. The remaining cells are empty, dot. Using this setup, we'll walk through the algorithm step by step to determine the number of pawns the rook can capture. In this example, the rook is located at position 2, 3, which corresponds to row 2 and column 3. First, we simulate its movement upwards. No pawns are encountered in this direction before reaching the edge of the board, so no captures are made. Next, we check downwards, where the rook encounters a pawn at position 4, 3. This pawn can be captured, so we increment the counter and stop further exploration in this direction. Moving left, the rook doesn't encounter any pawns before hitting the edge of the board. Similarly, moving right, no pawns are found before reaching the board's edge. After evaluating all four directions, the total number of pawns captured is 1. The result of this example is therefore 1. Additionally, we should consider edge cases, such as when there are no pawns on the board. In such cases, the result would naturally be 0 since the rook has no targets to capture. Other important scenarios to consider include the rook being surrounded by pawns. In this case, the rook could potentially capture up to 4 pawns, 1 in each direction, if they are adjacent. However, if there is another piece blocking the rook's path, any pawns located beyond that piece cannot be captured. These situations highlight how the rook's movement is restricted by obstacles on the board. While the brute force approach we've discussed is straightforward, it's also efficient for this problem because the board size is fixed at 8 by 8. Early termination in each direction, whether due to capturing a pawn, encountering an obstacle, or reaching the board's edge, ensures that we avoid unnecessary computations, making this solution both simple and optimal given the constraints of the problem. Here, we begin by defining a class called solution and a method inside it named numberRookCaptures. This method takes a single parameter, board, which represents an 8 by 8 chessboard. The first step is to locate the position of the rook on the board. To do this, we use 2 nested loops to iterate through each cell. When we find the cell containing R, which represents the rook, we store its coordinates in rook_x and rook_y, then break out of the loop. Next, we define a helper function called captures_in_direction, which takes 2 arguments, dx and dy, representing the direction of movement. Starting from the rook's position, we move step by step in the specified direction by updating x and y. If we encounter a pawn, represented by p, we return 1, indicating that a pawn can be captured. If we encounter any other piece, such as a bishop or queen, or move out of bounds, the function stops and returns 0, as capturing is no longer possible in that direction. If the path remains clear but no pawns are encountered, we also return 0 for that direction. Finally, we initialize a variable called captures to 0 and define the 4 cardinal directions, up, down, left, and right. For each direction, we call captures_in_direction and add the result to captures. This way, we accumulate the total number of pawns the rook can capture. The method concludes by returning the value of the captures variable, which represents the total number of pawns the rook is able to capture on the given board. This completes the implementation, and the logic ensures that we systematically check all possible captures in the 4 cardinal directions. With this approach, the solution is efficient and adheres to the constraints of an 8 by 8 chessboard. Here, we begin by defining the method numberRookCaptures that takes a 2-dimensional character array, board, representing an 8 by 8 chessboard. The first step is to locate the position of the rook, labeled as R, on the board. To do this, we initialize 2 variables, rookx and rookie, to -1, which will store the coordinates of the rook once found. We then use a nested loop to iterate through all rows and columns of the board. If the character at a specific position is R, we assign its row and column indices to rookx and rookie, respectively, and exit the loops. This ensures we stop searching as soon as the rook is located. Next, we define a helper method, captures_in_direction, which calculates whether a pawn can be captured in a specific direction. The method takes 2 parameters, dx and dy, which represent the direction of movement in terms of row and column offsets. Within this method, we use a while loop to traverse the board in the given direction, starting from the rook's position. At each step, we update the current position by adding dx and dy to the row and column indices and ensure the new position is within the bounds of the board. If the position contains a pawn, denoted by p, we return 1, indicating a capture is possible. If the current position contains any other piece, meaning it's not empty, we return 0 because the rook's path is blocked. If we exhaust all positions in the given direction without encountering a pawn or an obstruction, we return 0 as no capture is possible in that direction. With the helper method defined, we now calculate the total number of pawns the rook can capture by iterating over all 4 cardinal directions, up, down, left, and right. These directions are represented as an array of integer pairs, where each pair specifies the row and column offsets for that direction. For each direction, we call the captures_in_direction method, passing in the offsets, and add the result to the captures variable. After checking all directions, the captures variable holds the total number of pawns the rook can capture, which we then return as the result of the number of captures method. Here, we have a chessboard where the rook, denoted by R, is positioned at 2, 3. The task is to determine how many pawns, represented as P, the rook can capture. First, we locate the rook on the board by iterating over all the cells using nested loops. Once the rook is found at 2, 3, we proceed to check all 4 possible movement directions: up, down, left, and right. Starting with the upward direction, the rook moves from 2, 3 to 1, 3, where it encounters a pawn. Since the rook can capture a pawn directly in its path, we record 1 capture in this direction. Now, we move on to explore the other directions to complete the analysis. Next, we check the downward direction. Starting again at 2, 3, the rook moves to 3, 3, which is empty, and then continues to 4, 3, where it finds another pawn. This pawn is captured, making the total captures so far 2. Now, for the leftward direction, the rook moves to 2, 2, which is empty, and continues further left until it reaches the edge of the board without encountering any pawns. Therefore, no captures are made in this direction. Finally, in the rightward direction, the rook moves to 2, 4, which is also empty, and continues until the edge of the board, again without finding any pawns. With this analysis complete, the total number of pawns captured in this example is 2. In this second example, the board has a bishop, denoted as B, positioned at 1, 3, which blocks the rook's path in the upward direction. As before, we locate the rook at 2, 3, and begin by checking the upward direction. This time, the rook moves to 1, 3, and encounters the bishop, which blocks its path, preventing any captures. The capture count remains 0. In the downward direction, the rook moves to 3, 3, which is empty, and continues to 4, 3, where it finds a pawn. This pawn is captured, bringing the total captures to 1. For the leftward direction, the rook moves to 2, 2, which is empty, and then reaches the edge of the board with no pawns captured. Similarly, in the rightward direction, the rook moves to 2, 4, which is also empty, and continues to the edge of the board without encountering any pawns. Therefore, the total number of pawns captured in this example is 1. In the third example, the board is set up such that the rook is completely blocked by bishops on all sides. The rook is located at 2, 3, and we start by analyzing its movement in the upward direction. Here, the rook moves to 1, 3, and finds a bishop, which immediately blocks its path, resulting in no captures. With no pawns captured so far, we proceed to evaluate the other directions. In the downward direction, the rook moves to 3, 3, and again encounters a bishop, which blocks its path without allowing for any captures. Similarly, in the leftward direction, the rook moves to 2, 2, which is empty, and then reaches the edge of the board without finding any pawns. Finally, in the rightward direction, the rook moves to 2, 4, which is also empty, and continues to the edge of the board without encountering any pawns. With all directions blocked or empty, the rook is unable to capture any pawns in this scenario, resulting in a total capture count of 0. The time complexity of our solution is determined by analyzing the operations performed on the fixed 8x8 chessboard. First, we locate the rook's position by iterating through each cell of the board. Since the board has 8 rows and 8 columns, this requires at most 64 checks, which is constant due to the fixed size of the board. This step takes 1 time. Next, we evaluate the rook's potential captures in 4 directions: up, down, left, and right. For each direction, we traverse a maximum of 8 cells, which is the length of a row or column. With 4 directions, this results in at most 32 iterations, which again is a constant number. Therefore, this step also takes 1 time. Together, these operations ensure that the time complexity remains 1, as the board size does not scale. When combining both steps of the algorithm, finding the rook's position and checking potential captures, the overall time complexity is 1. This holds true for the best, average, and worst cases, as the number of operations remains constant regardless of the board's content. For space complexity, the algorithm's memory usage is minimal. The chessboard itself is part of the input, and its size is fixed at 8x8, so no additional space is required for storage. Auxiliary variables such as rook_x and rook_y for the rook's position, captures for counting captures, and directions for the 4 cardinal movements all use constant space. Thus, the space complexity is also O1, as no memory usage scales with the input. The algorithm does not involve recursion or require additional stack space, which further confirms that the space complexity remains O1. Comparing this approach to a naive or brute force method, we can see the efficiency of the optimized solution. A brute force method might involve iterating through all board cells multiple times or using nested loops to simulate movement in all directions. While the time complexity of such approaches would still be O1, due to the fixed board size, they might involve redundant operations, making them less efficient. In contrast, the current solution directly identifies the rook's position and performs targeted checks in 4 directions, reducing unnecessary computations and optimizing performance. This makes the solution both time and space efficient. Finally, let's solidify our understanding with a mathematical confirmation of the big O complexity. The maximum number of operations, 64 for locating the rook and 32 for checking captures in 4 directions, remains constant because the chessboard size is fixed at 8 by 8. These operations are independent of any external input size, as the problem constraints ensure the input dimensions are always the same. Therefore, the total number of operations is bounded by a constant value. This guarantees that both the time complexity and space complexity of the solution are O1, confirming the algorithm's efficiency. When solving this problem, there are several common mistakes to watch out for. First, it's crucial to account for all 4 cardinal directions up, down, left, and right when scanning for possible captures. Missing even one direction can lead to incomplete solutions and missed captures. Another frequent issue is stopping the search in a direction as soon as you encounter a blank cell, represented by a dot. Instead, you should continue scanning until you hit either a bishop or a pawn, as there might still be valid captures beyond the empty spaces. Additionally, forgetting to validate board boundaries can cause runtime errors. Since this is an 8 by 8 grid, you need to ensure that your indices remain within the range of 0 to 7 at all times. Lastly, avoid hard-coding assumptions about the rook's position. The problem often involves dynamic positioning, so your solution must be flexible enough to handle any valid starting location for the rook on the board. Inefficient traversal is another pitfall to avoid. Scanning the entire board repeatedly for each direction is unnecessary and can significantly increase the time complexity of your solution. Instead, you should stop as soon as you encounter the first obstacle in each direction. Now, when it comes to interviews, this problem is a great opportunity to demonstrate pattern recognition. It draws on principles similar to raycasting or line-of-sight algorithms that frequently appear in grid-based problems. Be sure to discuss edge cases, like when the rook is completely surrounded by bishops or when there are no pawns on the board to capture. This shows you're thinking critically about the problem. In terms of complexity, an optimal solution should run in O(n) time for an nxn board, as you only need to traverse the rook's row and column. Be prepared to explain why this is more efficient than an O(n)² brute force approach. Finally, anticipate follow-up questions where the problem might be extended to larger boards, multiple rooks, or pieces with different movement rules, such as queens or knights. Practicing these variations will help you adapt quickly during interviews. This problem is also closely related to other grid-based problems you might encounter. For example, LeetCode 1222, Queens That Can Attack the King, involves similar line-of-sight mechanics but with multiple pieces. Another example is LeetCode 994, Rotting Oranges, which uses BFS or DFS traversal in a grid to simulate spreading rot. Additionally, LeetCode 200, Number of Islands, emphasizes boundary checks during grid traversal, and LeetCode 36, Valid Sudoku, focuses on scanning rows, columns, and blocks for validation. When considering alternative approaches, brute force offers a simple but inefficient solution. By scanning the entire board to locate the rook and all pawns, you end up with O(n)² complexity, which works for an 8 by 8 board but won't scale well for larger grids. A more efficient method is optimized directional search, where you directly scan the rook's row and column, stopping at the first obstacle or capture. This approach is optimal with O(n) complexity and is typically preferred in interviews. For larger boards, you might consider using a hash set to store the positions of all pieces, which can speed up lookups. However, this comes with additional memory overhead and is unnecessary for smaller fixed-size boards like 8x8. Great job following through the problem. Today, we explored how to find the rook's valid captures on a chessboard, starting with a brute force approach. Remember, understanding the problem's constraints and iterating on your approach is key to efficient solutions. Thank you for watching, and we hope to see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!